already 3 minutes late. I hope people come on time. I see a large number of people come about 5-10 minutes late. That's not good. Somebody has their hand up. Can they write in the chat box what's going on? Okay, so I'm going to share my screen. Today is the third talk in this series of introductory talks, and till now I have, if you remember, can people hear me? Is that okay? I hope things are all right. If not, please write in the chat box. I so far talked about naked eye astronomy, how astronomers see the sky, and how it has been slowly dawning on people what the universe looks like. And then I started talking about measuring distances in the universe, and today I'll talk a little bit about measuring masses in the universe. And then we will, look at how we understand the large-scale structure of the universe. There is a hand up from Parthapratim Sharma. Can you just write in the chat box what your problem is? Please write in the chat box what your problem is. Thank you. And right, so we looked at parallax measurements and how the nearest stars. We first talked about how we can measure distances to the moon directly. Then, based on that, the sun, and based on the sun-Earth distance, we can build on that. That the sun-Earth distance is the basis of our measurement of parallaxes to the stars, and that leads us to looking at how much in the orbit of the Earth around the sun distances are the star moves on the sky, and as a result, they're measured. Now, let me just check whether yeah. So based on that, for example, we know that in the solar system here, which is called Sol in the middle, which is in technical language what the sun is called. And you can see that we know that the nearest stars, and these are all parallax measures, measured to them, how they're distributed around the sun. And it's interesting, then this is in light years, not in parsecs, but it gives you a feel for how empty space is, because you can see that the average distance between the stars is about a light year or so, and then even in the neighborhood of our star in the galaxy, things look pretty empty. And you saw when I talked about the zoom out movie, how you saw how these look different on different scales. I showed you that actually this measurement of parallax and measurement of distances became a very important exercise once we started doing this from space. And I talked about Hipparchus and Gaia last time. I just wanted to point out a couple more things. Hipparchus's entire lifetime was about 3.5 years, and it had an Earth-centric orbit, which is very close to the Earth. It came as close as 500 kilometers, and it moved away, as you can see, out to about 36,000 kilometers. And so this, you can see, changes the baseline from which you're doing parallax. And so also slightly, because the Earth is going around the sun. But it is also it was space, and so it close to the Earth. The limitation is of measurement, where the size of the image that you can get from the ground is blurred by variable refraction in the atmosphere. I'm going to talk about that at some point later on. The astrometric what happens here? The astrometric resolution of Hipparcos was 1,000th of a second, which you can never get from the Earth. Most by repeated measurements, you can go down to about a tenth or slightly below. So, and then it had another instrument which slightly had a better kind of instrument which targeted a lot more stars, but with slightly worse resolution. But Gaia has, of course, I mean, I told you it was actually 2019, 2020. By 2020, we had 1 billion stars being measured, and Gaia is going to lead this kind of activity later on. I mentioned Lagrangian points and things like that last time, but because it was towards the end, it was very difficult to explain. And clearly, there are a lot of questions from you about this system, so I thought I'd spend a couple more minutes today talking about it. If there are two attractors, the Sun and the Earth in this case, then for a third point, there are these points called Lagrangian points, where because the third object is going around, it has centrifugal force, and the centrifugal force plus the two attractions from the two objects, the Sun and the Earth in this case, the three cancel out in 5 positions, which are called the 5 Lagrangian points. And they have slightly different properties from each other. In some of these points, and any standard dynamics textbook will actually explain this to you, an object, a test object that is resting there will be in stable equilibrium, and in some of these objects it will be unstable equilibrium, which means that if there is a perturbation, it can drift off, whereas in stable equilibrium, if there's a perturbation, it can come back to the original position. As you know, India is sending its sun mission, Aditya, which will be launched next year, early next year, probably in January, to L1, which is going to be in between the Sun and the Earth and look at the Sun 24 hours. This Gaia goes to L2, which is on the other side. And so here is how, for example, it was launched from the Earth. Similarly, JWST had a similar thing. But in this case, it doesn't have a regular orbit. It's got this very complicated Lissajous orbit, because it just gives you a very large number of baselines to play around with in order to do parallax. Okay. So that's the idea. It is true that L2 is not a stable Lagrangian point. L1 is, but there are various reasons to choose L1 and L2. For example, if you took this and put it at L1, then of course it's much closer to the Sun, but also it will have the Earth block it because it's looking at the sky for most of the time. It is an important thing for a Sun mission like Aditya to be in L1 because it can look at the Sun without the Earth blocking it. So L2 is a much better place for JWST or Gaia because it can orbit an empty point in space, and it is not eclipsed by the Sun or the Earth most of the time, as it would be L1. Nobody's used L3 because it's hard to get there and stuff like that. So that's all the things I would say. If you want to know more about Lagrangian points, and there are questions coming in here, please go and just type it in Google, and there's a lot of resources on the web to find out. Advanced classical mechanics textbooks will tell you. Again, I will repeat, a Lagrangian point is somewhere where in this system, the gravitational pull due to the Earth, to the Sun, and its own centrifugal force because it's orbiting, all three cancel out, right? So there are 5 such points. Okay, so Gaia's mission then is to essentially from here measure the positions of stars out to the center of the galaxy and build a three-dimensional map, and that's doing this now. You will get separate courses on galaxies later on, but let me just tell you a little bit about our situation in the universe, because this is quite important in terms of what I'm going to talk about next. Because we were talking about measuring distances to the nearest stars in one thing is one thing, but when you want to measure distances and measure masses all over the universe, you have to know a little bit about what we are looking at. And so I'll spend a little bit of time talking about our position in the universe and a little bit in detail, and then I will go on to talk about dark matter and dark energy and things like that, and how measuring distances and measuring masses is very important for us to know about all this. And this is the substance of today's lecture and tomorrow's lecture, these two lectures. Okay, so we talked about the cosmological distance ladder, and we talked about parallaxes, where nearby stars. You can go out to a few tens of light years, and that is because the parallaxes themselves become so small, it is very difficult to do it from Earth. You can go far beyond if you are in space, like Gaia. But if you then want to make that into a very large number of stars for which you want to know distances, now you have to go to what is known as a primary distance indicator or a secondary distance indicator, which is no longer a geometrical distance indicator. Geometrical distance indicators give you distances directly without any assumption, whereas now, if you have to take another distance indicator for a faraway object, which will be calibrated on the geometrical distance indicators, it has to uh, rely on some kind of physics, which will have to have a model, and then it'll become model dependent. And these are called primary distance indicators. And things that are depend on a model, which again has to be modeled on the geometrical distance indicators, are called secondary distance indicators, like television, etc. So let's go on to the next step, and very briefly, I'm going to talk about. As you know, we said we have to depend on standard candles, so we need to know how bright something is in order to find their distances by measuring the light that falls. And I'll give you great examples later on in this sequence. But one of the first things I will tell you is that here is the example of what is known as the Hertzsprung-Russell diagram. And I hope you have started the courses on stellar astronomy, in which this has already been introduced. And this will be done in great detail, of course, in the lectures on the stellar astronomy. But you know that in what is known as the Hertzsprung-Russell diagram, all stars in our galaxy can be put on this kind of a diagram, in which the y-axis is the luminosity, which is the actual total amount of radiation that comes out of the star in units of watts, in units of ergs or joules per second. And so that's this, and you can see this is in a log plot. And on the x-axis is a measure of the color of the star, or the temperature of the star, because stars are black bodies. Their colors are related, of course, to the temperatures. These are just will tell you. Color is nothing but the ratio of two fluxes at two different wavelengths. Is called color, and this is fixed for a black body curve. And so the surface temperature essentially, and the spectral type of the star is a technical term that will be explained to you in the stellar lectures. It comes from a combination of the black body spectrum and the SAHA equation, the SAHA ionization equation. Together classify stars into different spectral types, which is exactly correlated with its temperature. So they are put together as the x-axis. And here on the y-axis, you can see on the right-hand side is the absolute magnitude, which is nothing but log of the luminosity. So they are related. So in this particular diagram, if you put stars, and you can see these are measurable quantities. You can, by looking at the spectrum of a star, you can fit a black body curve to it and find its temperature. You know, our sun, the star, our sun, is 5,800 degrees on the surface, right? So it emits a certain spectrum very nicely. You can fit it, and you can measure it, and you can put it here. Okay. Then comes the y-axis. Now, if you know what kind of a star it is, most stars, when they are producing normal fusion in their core and producing the energy due to fusion, they lie on this diagram called the main sequence. Our star, as you can see, this is calibrated such that our sun is it has its temperature here, 5,800, as I said, and on the y-axis it is 1, because all these are luminosities as a multiple or fraction of the luminosity of the sun. So the sun is 1 here, so these things are 100 times the sun's luminosity, these things are 10,000 times the sun's luminosity, etc. Okay? So the sun is here, and you can see if you, from the spectrum of a star, it tells you not just whether it is a main sequence star, which means that it is in a stable configuration where it is producing energy due to fusion in its core, which is its main span of life. Our sun, for example, will last for 10 to the power 10 years. It's halfway through its life now, just doing this, and it will spend on. It has been for the last 4.5 billion years, and it'll spend another 5 billion years on the main sequence here. So most stars are here, but not many other stars. I mean, there are many stars which are not on this main sequence, and these are as you learn from the stellar structure courses that as the star finishes its core burning of hydrogen into helium, it moves away from the main sequence and goes into the red giant branch and horizontal branch and all that kind of stuff. And so they're all over the place, and they're very famous stars like Arcturus, Betelgeuse, Deneb, Rigel, etc. They're all up here. But you can recognize that by looking at their spectrum and recognizing how they are. So if you know the star is main sequence, then just measuring its temperature tells you its luminosity, right? So that is, I told you before that here, standard candles, you need something that tells you what its luminosity is. So by measuring its flux, you can tell how far away it is. For main sequence stars in our galaxy, all you need to do is to take a spectrum and draw a black body curve, measure its temperature, and that tells you how much luminosity it has, how much power it is producing. If you can show it is a main sequence star, then you know where it is on here, its luminosity. Once you know its luminosity, you know its distance because you can measure its flux. Okay. If it is not a main sequence star, and there are ways of telling whether it's a main sequence star or not without knowing its distance, then that this method cannot be applied. You need other methods, some of which we will talk about later on. Okay, so what I'm going to do, just to show you, for example, Hipparcos in its first, the 3-year flight, measured, as I said, 100,000 stars. It produced this very nice HR diagram because it measured all these parallaxes. And so we know the HR diagram, just the opposite, because we know the distances here. So we know the main sequence, where it is and where all the other red giants are, etc., etc., etc. So now, if you're measuring the distance to an unknown star, we can find out. And yes, there's a question in the chat box asking for introductory textbooks, etc. We will help you find some. and we will also put some introductory textbook PDFs and things like that available for you. I'll talk to the organizers so that that can be done. Now, I told you that there is a basic problem in measuring the positions of stars, the sizes of stars from the ground, and this is something that I need to address. And that is as follows. You know, stars twinkle. Now, stars twinkle because stars are point objects. The actual angular size of a star, even the nearest star, is a very small fraction of an arcsecond. It is 10 to the power minus 5 arcseconds. You can work that out. You can take the size of the sun and put it at 1 light year, and you will see that its angular size is going to be 10 to the power minus 4, 10 to the minus 5, 10 to the minus 6, something like that, arcseconds. So it is essentially a point object. It's very, very tiny compared to the distances we measure. Now, you can see that the star's light comes and comes through the atmosphere. And it comes to a telescope or a human being, but it passes through 100 kilometers of air. Now, each layer of air has a different temperature, pressure, and density. And it's also moving given the time of the day. In fact, if you sit at any point in the atmosphere, things are changing of the order of many times a second. So the refractive index, which is a function of temperature, pressure, and density, is changing. So this poor beam of light that is coming to you, you can see, is coming through all these different layers, and they're all changing, and it's being refracted, and the refractive index is changing. So it comes in a zigzag path to you. Not only does it do that, if it forms an image, you can see within a fraction of a second, that starts moving around. Because the refractive index there is changing. So our eyes can integrate for 1/10 of a second. And then that 1/10 of a second, the next 1/10 of a second, things are moving around. That is why stars twinkle. Planets don't, because planets are much bigger. And so they're averaged over the planet's disk. How does that affect us? It is because when we take an image of a star to do the photometry, then you have to average over a large time, because, for example, I can take an hour's integration and a night to take an image, many hours, and over that the image shifts. Okay, and as it shifts, then it blurs the image out, and this is known as seeing. And in a place like Pune, if I have a telescope here, and I do, just on top of my building, the image of a point object like a star, whose actual angular size is a very small fraction of an arcsecond, will be a few arcseconds, like 3, 4, 5 arcseconds, because the air here is always moving, and it's blurring out the image. At the best observatories, this is of the order of half an arcsecond. The best I've ever taken from a great observatory is maybe 0.4, 0.3 arcseconds. So that, if you compare with the kinds of parallaxes that you're trying to measure, and you can see, you can never directly measure 0.02 arcseconds of parallax, right? You can do that by repeated measurements, and so you bring down your errors by square root of n, as you know from repeated measurements. And this is how people achieve this, but you can't get very far. And this is why we need to go to space. It is going to affect a lot of other things we will look at in the rest of the course, and that is why I thought I'd explain to you this particular thing. So I'll go back to the Herschels I talked about, and this is because somebody asked me the question, how did Herschel's telescopes look? William Herschel was building these telescopes in his backyard. Carolyn, his sister, was actually looking through the telescopes as an amateur astronomer too. and she discovered 8 comets. William Herschel didn't discover any comets, but he, of course, discovered a planet, which made him famous. And then he became famous as an astronomer by discovering Uranus. And then he went on to also become an astronomer in addition to being a physician. His son, John Herschel, actually was born in England, and so William came from Germany and was as a musician. And he went on to build bigger telescopes, and he took his father's telescopes to the southern hemisphere, to South Africa, and started looking at the southern sky, and slowly we built up a picture. And I told you this, and I showed this picture to you before, that between William Herschel and Messier, they had worked out that there are two different kinds of stars. The stars that are they twinkle, they're point-like, and then there are fuzzy things in the sky, which are they thought were two different kinds of stars, right? And we, as I said, now we know by measuring distances that some of these stars are actually single stars, some of these stars are clusters of stars, and some of these stars are these things called galaxies. So this is something that we know only from the 1930s, is the fact that the universe is made up of galaxies. And you will receive separate lectures on galaxies, and I'll come back later in the course to talk about groups and clusters of galaxies. But think about it this way. The universe is made up of basic units, like matter is made up of molecules. These basic units are called galaxies. And galaxies themselves have billions to hundreds of billions of stars in them. And we live in such a galaxy. There are galaxies that are nice and round called elliptical galaxies. About 75% of all galaxies are flat. They are disk-like galaxies in which you see spiral structure. Galaxies they don't like to live alone. They live in groups, and they interact with each other. They merge with each other. And we use a lot of human terms to describe their interactions. They harass each other. They strangulate each other and stuff like that. But they are always, and I'll show you examples of that. So galaxies, and I needed to introduce this to you to talk about how then we go outside our local star system and make measurements about how big these galaxies are, how massive these galaxies are, what they're made of, and how far away they are. They're all connected questions. And we've been doing this only in the last 100 years. This is an extremely new subject. Our own galaxy, the Milky Way, and you'll hear more about that later on in the course. There are talks on the Milky Way, there are talks on galaxies. But let me give you, my job is to give an introduction to all of this, is that our galaxy looks like this. Somebody asked me, are these images captured or imaginary, just artistic? I will point out which is artistic and what is imaginary and what is real. Here, these two images, of course. So here, all of these are real images. Why will they be artistic? Go and look them up. These are all real images of galaxies. This cannot be a real image because this is a picture of our own galaxy. We are inside it. So we can't go out in the galaxy and take a picture. So these are artists' impressions. You can see that this is a galaxy that is we are a flat. As I said, 75% of all galaxies are flat, like a chapati. They have a little bulge in the middle, also like a chapati. And so we are a planet around a star, which is nowhere near the center, 8 kiloparsecs away. That's 25,000 light years away from the center. The entire size of the galaxy is 50 kiloparsecs, which is you can work out 150,000 light years. So these are all stars. Now you can see that in the plane of the galaxy, the disk of the galaxy, there's a lot of dust, and that blocks the light, and this is why it looks dark. Now, when you look at the galaxy from top, like here, and again, this is because we have now reconstructed the three-dimensional distribution of stars. We can plot things like this and draw things like this. And we can look at other galaxies that look like us. So we know that our galaxy has at least 5 of these spiral arms. They rotate very fast, and so they have spiral structure. We are right now near the Orion arm. And remember, that's 25,000 light years away. Okay. Now, and the questions that people are asking about why galaxies are flat and not light, not round, etc. You will get whole lectures on galaxies. I'm not going to go into that now. Very, very good reasons for it. It's very, very interesting subject on its own. Why galaxies look like the way they do, why the spiral arms are there. These are excellent questions which people have done a lot of research in the last. This is what the Milky Way looks like from inside. Okay, so when you are here and you're looking, so think about it. You're looking out into the universe with or without a telescope. When you're looking at the stars in the sky, you are looking in a direction like this. So you're actually looking at this thin layer of stars that is in the disk. So you can look in that direction, that direction, that direction, and you're looking at that thin layer of stars, and those are the stars you see, right? So after a point, the stars run out, and you're looking into empty space. But if you look in that direction, towards the center of our galaxy, you remember a few days ago the picture of the black hole in the center of our Milky Way came out, and that's right here, right in the middle. And you're looking at towards Sagittarius. You're looking towards that. It so happens that Sagittarius is actually very low in the sky from India. In order to study the southern hemisphere much better, you have to go to the southern sky and Sagittarius, etc. much better. You have to go to the southern hemisphere. From India, it is very, very low in the sky because the Earth blocks this part. But this, how would this look like? Because you're looking towards the bulge of our galaxy, it looks like a band across the sky, and this is what it looks like. So this is now a real picture. This is not an artist's picture. It's a lot. This is in northern Chile, on the Andes Mountains, and on the Andes Mountains in the Atacama Desert, where a lot of the fantastic telescopes are. This is one of the telescopes that will become a very important telescope in the story I will tell later on. But this is the 4-meter telescope on Cerro Tololo, and I've been there 20 times. It's a wonderful, wonderful place. And at night, when you are there, you can read by starlight. You don't need the moon, and that is because the Milky Way is up there. This is called the Milky Way. You can see the band. It's called the Akash Ganga in Indian languages. It's like a river in the sky. And in the Western, in the European languages, it's called the Milky Way. And you can see these black patches of dust in there. This is where the galactic center is, and the black hole is somewhere in the middle of this black patch. Okay. Now, there are 2 other things you see in the sky in this particular picture, and these are these 2 patches. And these are called the Magellanic Clouds. They're called clouds. They look like clouds, but they don't go away. They are actually galaxies. They are moon galaxies of the Milky Way, the satellite galaxies of the Milky Way. In fact, our own galaxy we know of about 40 such satellites. Like Earth has moon, our galaxy has satellites that go around it. And these are the 2 nearest ones. They can be seen with the naked eye. From India, we can't see them. If you're anywhere in the southern hemisphere, you look up, it's always there. So these are naked eye galaxies. We'll come back. We'll look at them in a little while. But this is the view from the southern hemisphere. We are not so fortunate in the northern hemisphere to see most of the Milky Way, but you can, if you go to a dark area, you can see this very nicely, our own galaxy from inside. So we can look at other galaxies that look like the Milky Way. So these are galaxies that look like the Milky Way, right? This is an actual picture, not an artist's impression, of another galaxy that looks like the Milky Way. You can see 5 arms, and you can imagine that our galaxy looks like it if you were looking at it from outside. And then if you're looking at it at different orientations, you can see that this is a side-on galaxy, which is a spiral galaxy, or you can look at it flat on like this, like we see our own galaxy. Our own galaxy, because we're in the center, we see it edge on. And this is another galaxy outside that we are seeing edge on, and you can see how that looks like our galaxy. And if you take that, that's exactly what our Milky Way view is. This is a picture, actual picture taken of our own Milky Way. And you can see that's what it looks like, because we are now inside and we're looking at it edge on, and the dust lanes are in the middle, right? I hope that makes sense. So now you can see how, and the fact that we are looking at a galaxy, just because we didn't know the distances to these things, we know only for less than 100 years. This issue, this debate was resolved in the 1930s by Hubble's work, which I'll talk about. So going back to our knowledge of this, here we are in the galaxy 25,000 light years from the center, and we are actually going around. Our galaxy, spiral galaxies turn, but the stars themselves go around much faster. Okay, so let's figure out how we are going around in our galaxy. So if I ask you the question, how long does it take for the sun to go around our galaxy? Actually, the spiral pattern turns very slowly. The actual galaxy turns slowly compared to the sun's going around. So it's not the stars that are moving with the galaxy. The pattern moves at a much smaller speed. And I hope in the lecture on galaxies this will be taken care of. But I'll do a simple calculation to see how you can do this. The sun is traveling. This can be measured very easily. It has been measured, and it will take me another lecture to tell you how it is measured, but it can be measured. And I'm telling you the answer. It is traveling at a speed of 220 kilometers per second. You're not feeling it, right? It's dragging the Earth with it. The Earth is going at 30 kilometers per second around the sun. The sun is going at 220 kilometers per second in a circular orbit, okay, at a radius of 8 kiloparsecs, 25,000 light years, around the center of the Milky Way. It's a circular orbit, okay. I say mostly circular orbit because it actually has a motion in the other direction as well, which is much slower. It has a direction in the z direction, so it's actually going like that. But the frequency of that is less than the circular frequency. So I won't talk about that now. But the sun is going around. So from this, it's easy for you to calculate now how long it takes for it to go around the galaxy. Just do 2 pi r divided by v. Now, if in order to do the calculation, I can do this in my head, because even though if you do 2 pi r divided by v and you put r as 8 kiloparsecs and v as 220 kilometers per second, you will have to convert parsecs into kilometers, and seconds into whatever years, and all that conversion takes time. I use a very convenient system of units, and this is the one astronomers use. And since you will be doing some astronomy, I can teach you this. Every subject has its own way of doing little tricks that people can do numbers in their heads. For example, if you're a particle physicist, you put h bar equal to 1, or c equal to 1 if you're a general relativist. I put g equals to 1. In this calculation, g is not needed, but when I do mass calculations, g is needed. So in any system of units, there are 3 basic units, right? Mass, length, and time. So you can choose 3 arbitrary things, and then everything will depend on it, right? And so you can create your own system of units. You can fix 3 things in your head. I fixed g equals 1. I fixed the unit of distance to be 1 kiloparsec, because that's the scale that matters in a galaxy. And I fixed my unit of velocity to be 1 kilometer per second based on these numbers. Once you fix that, you can't fix anything else. Everything will depend on it. It turns out, if you put g equals 1, you put 1 kiloparsec as a unit length, and another unit of length as velocity, 1 kilometer per second. Then the unit of time, which comes from these two, becomes exactly a giga year. 1.97 times 10 to the power 9 years. The price you pay, that unit of mass, becomes 2.3 times 10 to the 5. That's one thing you have to remember. Right? So, but with this system of units, I can just do this. I can do 2 pi r. So my unit is 1 kiloparsec. So my distance is 8. 2 pi is 6 times 8 is about 50. 2 pi r. Right? Divided by 220. So that's about roughly about 1/4. So my answer is 1/4. 1/4 of what? Unit of time is 10 to the 9 years. So 1/4 of 10 to the 9 years. Right? So it's about 1/4 of a gig a year. The sun to go around the galaxy. How long has the sun been alive? The sun has been there, alive I say, but how long in existence? The sun has been in existence for 4.5 times 10 to the 9 years. So in its lifetime, in its age, it has gone around about 20 times the galaxy. Right? And it will go around the galaxy another maybe 25 times or 30 times. Okay. So this gives you a time scale of the fact that the sun has actually gone around quite a lot, and it's passed a lot of these different things that you see. It has gone around and encountered. At some point, it was in the Cygnus arm. Sometimes it was in Sagittarius arm, etc. Just like that. And the rest of the galaxy turns very slowly. Okay. So I hope that makes sense, and that gives you an idea of. Now, there are questions in the chat box asking, does the Milky Way go around anything? Of course it does. I'm going to tell you in a minute. And is the black hole always in the center of the galaxy? Supermassive black hole is always at the center of the galaxy, unless the galaxy is crashed into another galaxy and caused it to move a little further away, because the galaxy, as you will see, has a huge gravitational potential well, and the black hole sits in them. And it's the most massive thing in the galaxy. Okay, so what does our local neighborhood look like? Our local neighborhood is called the local group, not very imaginative name. Here's the Milky Way with some of its satellites. As I said, there are about 40 or so we know about. This picture shows only a few. You see the LMC and the SMC, the two things you saw in the sky in the picture from Chile. There are others. And then our nearest big galaxy is called the Andromeda Galaxy, which lies here. It's about 0.7 megaparsecs away, megaparsecs, million light years. So it's 0.7 million parsecs. So it's about 2 million light years away. And it's got its own entourage of satellites. We know of another 40 or so satellites that belong to Andromeda. And we are discovering these satellites every day because, I mean, they're very faint things and it takes a lot of effort to find these things. Okay? And these two are falling towards each other. And if you zoom out a little, so these two, the Milky Way and Andromeda, are in an almost linear orbit. They actually have a very little angular momentum. So somebody asked me, well, is Milky Way going around something? It's actually falling towards something. It's in a straight line orbit. And this whole thing is moving also, right? And that whole thing is moving. Nothing is stationary in the universe. Yeah. The fact that this is a straight line orbit and has very little angular momentum was the substance of half of my PhD thesis 35 years ago, right? So this is something I showed, and this is a very recent knowledge. We are only finding out about such things. So and then, as I said at the beginning, the web-like structure on which these galaxies are moving are much larger, and the galaxies are in pairs or in threes or in fours or in fives or in great clusters, and this will be the subject of the two talks I will give at the beginning of June when I talk about groups and clusters of galaxies, and then much larger scale. So let me tell you a little bit about the local group. I said that we have these groups of galaxies around the Milky Way and Andromeda. I'll show you some of these to show what our satellite galaxies look like. You remember the Large Magellanic Cloud and the Small Magellanic Cloud, right? This is what they look like. This is actually a real picture, again, but taken in the infrared so that you can see a little more of these. If you zoom in on the Large Magellanic Cloud, this galaxy, you will see it's a very irregular galaxy, and it's got quite a lot of patchy things. So it turns out that the dwarf galaxies, the galaxies that are satellite galaxies, small galaxies, often don't have any regular shape. They are not nice and round or flat. They are irregulars. And because they are small galaxies around much bigger galaxies, they're often being tidally perturbed by the big galaxy. And you understand tides, right? Tides mean that gravitational force on different parts of the galaxy are different from the big galaxy. And so they cause perturbations and make all kinds of things happen. For example, they cause new star formation to happen. And all this will be the subject of lectures to come. You can see star forming regions here. This is a real picture. Somebody asked me whether I'm showing artists' pictures. It's all real pictures. The LMC is very big on the sky. Compared to the size of the moon, you can see it's 4 degrees across. The SMC, for example, the Small Magellanic Clouds. The Sagittarius galaxy is actually, the size is 270 degrees across the sky. And that is because it got so close to our galaxy that it is being torn apart by our galaxy by tidal forces. And so it is falling into our galaxy, and it's a galaxy that is being torn apart. So you see it as an arc falling into the galaxy, right? And it's wonderful. And this was discovered only in the last 20 years. And you can see as you go to faint to smaller and smaller galaxies, they become fainter and fainter and fainter. And once you go to the really smallest dwarfs, you can barely make out. And you need advanced image processing techniques to actually extract the galaxy image. So that's our local neighborhood. So I told you about the galaxy in the Milky Way. Here's a little a simulation that my friend John Dubinsky made of what somebody asked, what is our galaxy going around? There is this the orbit of our galaxy and Andromeda. It's coming towards each other, as I said. It's actually falling towards each other at about 120 kilometers per second, and it will merge together to form one single galaxy in about 4 billion years or so. This is something I wrote in a paper, and so John starts his movie, which is actually available on YouTube. You can look it up later on to show what's going to happen, because what they've done, what he and his group has done, this is in Toronto, in Canada, they've taken stars and matter and whatever dark matter in these galaxies, put them together, put them in a simulation, and showing what's going to happen to our galaxy in the future. So it's interesting to see that. So starts off with a quote from my paper saying that in about 4 billion years, they will merge because they don't have enough angular momentum in the system. And you can see these are the two galaxies. One is Andromeda and one is the Milky Way. And in about 4 billion years, this is what's going to happen to them. This is a simulated view. You can see they go past one another and they disrupt each other. So they spread around, then they come back and then slowly merge with each other. And this particular simulation, and then the nuclei go. So you can see the two black holes in the centers are displaced from each other, and then they eventually will merge. Right? And you see this happening all the time. You see this because this whole thing will take 4 billion years to happen. In 4 billion years, it will take probably 1 billion years to happen, this whole phenomenon. But you can see this happening now in other galaxies. Right? You can see closely interacting galaxies that look like this. They actually, when the galaxies collide, the intergalactic gas collides, the stars go through each other and they come back and stuff like that. And so, for example, here is an example of a nearby system. I showed you this in another context before. On the right-hand side, you see them in a normal optical picture, where you see M81 and M82. As you look at them in a radio image, an image that involves the hydrogen gas that's in the galaxy, you can see that there is another galaxy here, and all three of them are now interacting with each other, right? And you saw the simulation of how they interact with each other. And this is happening here now. This guy is pulling out gas from here, it's pulling out gas from here. And stars are also, you don't see those stars. They're tiny streams of stars that are connecting all that. And in tomorrow's lecture, when I talk about star streams at some point, I will show you pictures that have been taken of star streams connecting all these galaxies. So in the last few minutes, I want to talk about our measure of what is there in the universe, what the galaxy is made of, how do you measure the masses of these galaxies, and how do these distance measures allow us to measure such things as to how much energy and how much mass there is in the universe. That's the next topic I should go to. But I am going to first look at what kind of questions there are. I think I'm glad that people are answering some of the questions on the on here. There is no moon galaxy. I just gave a satellite galaxy a name. Satellite galaxies are galaxies that orbit bigger galaxies. Answer that is being given there is not strictly correct, because galaxies that orbit the Milky Way are satellites of the Milky Way, but each galaxy, each big galaxy in the universe has satellites that go around them. And so satellite galaxies are just galaxies that go around other galaxies, bigger galaxies, just like satellites in the in the solar system go around planets. Quickly, why does the speed of the sun differ for that of the whole galaxy? And this is something that you will hear when you're given the course, the little bit of lectures on galaxies. The pattern speed, the spiral speed of the galaxy is different from the actual things of the stars. And this is because the spiral arms, the pattern that you see, are not made up of the same stars. They are actually a pattern that is set in the dynamical pattern of the galaxy. And stars go between the patterns. And they slow down when they're passing the spiral arm, and then they speed in between the spiral arms. And because they slow down during, it's like if you think of taking a picture of a highway that's connecting Bombay and Pune, say, and you will find that there is a whole stream of cars, and there are places on the highway that seem to have a lot of cars, and those are where the traffic jam is, right? So cars are going on a highway and they slow down where there's a traffic jam, and they speed up and slow down. And so if you take a picture, you will find that there are concentrations of cars. And if you take the same picture an hour later, 2 hours later, you'll see the same concentrations, but they'll be different cars, right? Because those are the places cars have to slow down and things like that. So in a galaxy, when you see the spiral pattern, the stars are moving very fast, but those are places where there's a concentration of stars, and the star has to slow down and then it goes up. And I calculated the average speed of the star by looking at 2 pi r over v, but that's a very naive calculation. You can do a real calculation of exactly at what point the star's speed will be, etc. Okay, so I hope that answers the questions you have, and I hope that in the galaxy lectures you will be right. Yes, and I think most of these are questions for future lectures. So I'm going to start talking a little bit about, because this is the last bit that I'm going to handle, talk about dark matter and how most of the matter in the universe and in the galaxies are not seen, even in pictures like this, and how do we measure this? So the idea is that, we have to figure out what we are made of. We know that we are made of these things that are in the periodic table: carbon, hydrogen, nitrogen, oxygen, sulfur, etc. And the question can be asked is, we are made up of certain things. I mean, these are the periodic table elements, are the elements that are called baryons. They are made up of protons and neutrons in the nucleus and electrons around them. And they are in turn made up of quarks. And things that are made up of quarks are called baryons. So we are made up of quarks. Is the universe made up? This is a question that started to be asked in the middle of the last century, right? Until then, people thought, yeah, of course, I mean, we are made up of that. If you look many, many thousands of years ago, hundreds of years ago, people thought that, oh, the high heavens are made up of something else, right? The ancient Greeks thought that the heavens are, anything you see in the sky is made up of something different from ours. And Galileo, through his telescope, showed that the moon is exactly the same as the Earth. You have the same kinds of craters and mountains, etc. And then slowly we figured out that other things in the sky are actually very much like the Earth. And then came the era of physics when we found out that the physics that we have here applies to out there. But then comes a period when you can ask the question, you can understand a lot of the light that comes from the other things in terms of electromagnetic radiation, and the electromagnetic radiation is produced by particles that are made up of quarks and their leptons and things like that. But is the universe made up of these things, or it is made up of something else? So the answer is surprising, and this has only emerged in the last 50 years. So to do that, I need to introduce a couple of very simple dynamical concepts, and I'll come to this issue in the next lecture, which is tomorrow. So you know that if you take a solid rotating disk and rotate it at a constant angular speed, then you can plot speed against distance, and it will look like a straight line, right? Because angular moment, the angular speed omega is constant, and so v is proportional to r, right? So this is called solid body rotation. But a galaxy is clearly not a solid body. As I said, different stars at different distances, they're moving at different speeds, right? So how does the thing turn? Even in the planetary system, this is not right, because you know that the sun is in the middle and each planet is going around at a different speed, and this is governed by Kepler's laws, which we have all studied in college. And so, and there, you know from Kepler's laws that if you just take, because in the solar system, all the mass is in the center, and the planets are going around, and they're much smaller, so they're test particles. So they're going around, their speeds will be proportional, such that v squared is proportional to 1 over r. Right? So v would be proportional to 1 over square root of r, and this is what you see here, right? So what does the galaxy look like then? Is the galaxy like the solar system? Is the center of the galaxy the black hole in the middle and the bulge in the middle? Does it have most of the mass, like the solar system, and these planets going around it? The answer is surprising, and the answer is it is not. When I come to this next time, I will show you that what happens in the galaxy is that from the center, the rotation curve, which is the velocity as a function of radius, goes up as proportional. So the center of the galaxy, which is the bulge portion, is actually rotating like a solid body. But then it was found in the 1960s that the rotation curve kind of flattens out. It never falls off as it should, as 1 over r to the power minus 1 over r to the power half, but it stays constant out to a very long distance. If the galaxy really ended here, then outside it, as you know from Newton's laws, if you're outside a system, then you can treat a gravitating system as a point object. So this should fall off as 1 over r to the power half, and it does not. Okay. So I'll start from here in the next lecture. Meanwhile, let's see if there are any questions. People are asking amazing questions like, what is swing amplification? When I'm teaching you ABC, somebody's learning Shakespeare, certainly you will come to this when, I hope, in the lecture on galaxies. But but certainly this is something, that kind of stuff is taught only in graduate courses and beyond. I'm stopping share now and looking at questions. Somebody's raised a hand. Okay, I've unmuted you. Go on and ask me the question.
Hello, sir.
Yes.
Sir, my question is that when two galaxies were collapsed, then the origin of the galaxy would be merged, or there will be two origin made when after the collision.
I don't understand what you mean by the origin. Can you say that again?
Sir, I said that if our Milky Way has a particular horizon origin, then
Yeah.
after the collapse with Andromeda, so there will be created two origin, or the two origin will be merged, and it will be created a new origin for the new galaxy.
So what happens is that I will show you later on that actually the galaxy is sitting in a very large halo of matter, which is called dark matter, which has much more matter than the galaxies themselves. And so there's a lot of gravitational potential, and it goes at the center of the galaxy. The gravitational potential is very deep, gravitational, and so mass always goes and settles there. The most massive things will settle there. So once the two galaxies merge, and they will have one origin, because it will all mix up and become a much more uniform object. In fact, in the evolution of galaxies, and this is something other people will teach later on, we now think that the elliptical galaxies are formed from the merging of spiral galaxies. What happens is the spiral galaxies have angular momentum, and another galaxy has spiral. Angular momentums are vectors, as you know. And so when two galaxies with angular momentum merge, their angular momentum in general cancels out. So as these mergers go on, the angular momentum of these systems are destroyed. And as a result, what's keeping it flat is the fact that it's rotating. If free rotating object is flat, and as the angular momentum reduces, things puff up to become more and more spherical. So the spherical galaxies are galaxies that are resultant of the mergers of these galaxies. And this is something that you will learn in the evolution of galaxies later on. Okay. So, and in all of these mergers, what happens is that they merge to become one galaxy, and then in the end, many galaxies might merge to become one. There's another hand up, Apara. Please, I'm unmuted you. Go and ask your question. And I'm looking at the Google Sheet as well.
Yes, sir. Good
Yes.
evening, sir.
Yeah.
Sir, I just wanted to know, means if some meteor or some heavy object is coming towards Earth, or means Earth, then is there any technique which could change the path so that it couldn't just get in free fall to Earth, as like at the time of dinosaur happened and all that?
Yeah, it only happens in movies. Bruce Willis can do it. How can you change? I mean, there are very interesting ideas that have come on how to change the trajectories of things that are coming towards the Earth, and this is why we look out for asteroids and meteorites and things like that. Meteorites are small things that get burnt in the atmosphere. Asteroids are bigger things, like the one that destroyed the dinosaurs. The one that destroyed the dinosaurs, I don't think we could do anything about. There are some ideas that have come up, which have been already explored in science fiction and in movies, is that you can send a nuclear bomb out there, and which can embed itself in there and then explode before it hits the Earth, and things like that. But something as big as the one that killed the dinosaurs, if it's really approaching the Earth, we don't have the technology to do it. The best we can do is look out for them and hope they don't hit us. I think that's the best answer. But there are clever things. I mean, this is always a wonderful project to give to students, or competitions and things like that. And people come up with wonderful ideas. Some of them are feasible, some of them are not. But there's not much we can do. We are pretty helpless beasts on this planet. Akshat, go ahead. Akshat?
Sure. Hello, sir.
Yeah.
So my question is that when you mentioned that most of the mass of the galaxy is not concentrated at the center, so does it mean that the Sagittarius A star is not responsible for the rotation of the galaxy?
Absolutely not. The rotation of the galaxy is an angular momentum because it formed from a cloud that had angular momentum. You can't destroy angular momentum. It collapsed to form the galaxy, and its angular momentum, as you know, if it's a large thing and it collapses, it rotates faster, and so it has an angular momentum. The Sagittarius A star black hole's mass is 10 to the power 6 times the mass of the sun. The galaxy's mass is 10 to the power 12 times the mass of the sun. So the mass of the black hole is minuscule compared to, it's nothing like the sun being 95% or 99% of the mass of the solar system. Right? So the black hole is not spinning us around. Absolutely not.
Okay,
Black
sir.
hole is sitting, the black hole is sitting there. And you saw some stars. I mean, the Nobel Prize 2 years ago was given for finding stars around that black hole that are going around them, around that black hole. And from that, the black hole's mass was measured. But it's only those stars that are around the black hole, very, very close to the black hole. So I'm looking at the Google sheet, and I don't have much time, so I'm just going to answer one or two more questions. I'm looking at the Google form, and I am looking at Bharti from Bhavra Patil College, who has asked, in your slide, you've shown stars grazing in circular orbit at North and South Pole. It looks like, which slide? I don't know. Can you explain this? I don't understand this. I'm not going to answer questions on conditions necessary for life because I'm not talking about it. If Milky Way and Andromeda collide, they will pass through each other. Somebody is hurt. Shankarshan has talked about it. I just showed you a simulation, right? That's the best simulation that there is. The stars will pass through each other and then will come back again, and slowly they'll merge. Okay, and that's the best we know so far. And of course, they'll merge into a galaxy, one galaxy, but it might take a few passes. Vidyashagor University, Mendapur City College, asking the fact that Andromeda Galaxy is approaching the Milky Way. What's happening to the Big Bang? Why we talk about the expanding universe? Why are two galaxies coming towards each other? Wait till my lecture tomorrow. We're going to talk about this. That's a good point to stop today. I will see you tomorrow at the same time. Bye for now. Thanks.